Imagine you're responsible for a multi-site broadcast network, 2 or 3 facilities, production in all of them, and monitoring across all of them, and contribution feeds are shared. Now, one of those sites disappear. Not a switch, not a circuit, the entire facility. Your transport infrastructure survives, links are up, routing is running, no problems here. But Site 2 can't see sources that were registered in Site 1, and Site 3 can't either. And nobody can tell you how long before they come back. That's not a multicast forwarding problem. That's a source discovery problem. And it's the failure domain that most multi-site broadcast networks that don't really stress test. When a receiver joins a multicast group, something has to tell it where the source is. In any source multicast environments, that thing is the rendezvous point. The rendezvous point is protecting against an assumption. The assumption is very simple. Source discovery is available. Most multi-site networks test transport resilience, maybe link failover or a routing path failover or WAN redundancy. Far fewer have tested what happens when source discovery itself becomes unavailable. When transport fails, indeed traffic stops and everybody knows immediately. But when source discovery fails, traffic keeps flowing for existing sessions. New sources, however, will become invisible. And that kind of failure is silent until someone asks why they can't find a feed that should be there. That's the gap we're talking about here. In PIM sparse modes, receivers join a shared tree rooted at the rendezvous point. They don't know where the sources are. That's what the RP does for a living. When a source becomes active, its designated router encapsulates that traffic and sends it to the RP in a PIM register message. The RP decapsulates this, installs an S,G state, and triggers joins backwards towards the source when a receiver asks for it. And receivers can now find this. Every part of that process depends on the RP. One RP, one failure domain, of course. One maintenance window or one power out event and one hardware failure can make this a disaster, and source discovery eventually stops. A single RP in one site means sites 2 and 3 depend on site 1 for source discovery. Every source registration crosses facility boundaries. Every new feed depends on a single facility. Few articulate it this way, until incident review, of course. That's what RFC 344.6 solves for. PIM-SM, as originally defined, allows one active RP per group. So what's the consequence of having a single RP? We get traffic concentration, slow conversions when the active RP fails, suboptimal forwarding, and distant RP dependencies. If we have sources and receivers in Europe and an RP in the US, traffic has to cross the Atlantic twice, once to reach the RP and once back down the shared tree. That is not theoretical, that's a real operational failure mode. In a multi-facility environment, this plays out as follows. Sources in Glasgow and receivers in London, and the RP is in Manchester in our example. All registrations would go to Manchester, and all the discovery updates depends on Manchester. Anycast addresses that inside each facility and across facilities. So Anycast solved the single point of failure problem. Sources near site A, they register with the closest RP, and sources close to site B register with their closest RP. Effectively, no facility depending on another. That's great. That's a great solution, but let's stop here for a second and think what we've solved. we have 3 facilities, 3 RPs, 1 in each facility. Each source registers with its closest RP. And now we got 3 independent views of a multicast environment. And there is no synchronization between those RPs. An RP in facility 1 knows about sources registered to it. An RP in facility number 3 knows about sources registered to it. Neither know what the other knows. A receiver in one facility hitting its local RP has no visibility of sources registered to another RP. We've removed the hardware dependency, but we created a discovery and knowledge dependency. At a facility level, this means that the receiver asks London, for example, about a feed that originated in Manchester or Glasgow, and that RP has never seen that source. That join goes nowhere. So Anycast gave us redundancy, but gave us no source visibility in different multicast domains. And that's exactly what MSDP solves for. MSDP works by having a peering relationship between RPs in different domains, and they exchange a source active message. Once a source registers with its local RP, a message is fired from said RP against its peer to notify it of the availability of a specific multicast sender. MSDP has a few constraints that we need to account for if you decide to configure it. MSDP peerings must use unique unicast address and never the Anycast one, because that's included in the packet. Because the Anycast address must never appear as the RP address in the source active message. The reason is because when an SA message arrives at the peer, it runs a check. Did this message come from the right direction, from the right source? That RPF check uses the RP address in the source active message to determine the answer. If the Anycast address appears there, the check has a problem. The Anycast address resolves to multiple physical RPs effectively, and the check is not deterministic at that point, and it fails, and the source active message is dropped, and the source knowledge disappears silently at that point. And this is a configuration misstep I found in real broadcast networks. MSDP is often described as an RP protocol, and I believe that description is incomplete. MSDP is a source visibility mechanism. It is a way to connect multiple PIM sparse mode domains together. Each domain uses its own independent rendezvous point. Domains don't depend on each other's RPs, but they share source knowledge using MSDP. That sharing is the point. MSDP runs over TCP on port 639 typically, and it provides reliable delivery. It doesn't need to implement its own because it rides over TCP. When the RP first learns of a new source via PIM register, it constructs a source active message. 3 fields basically: the source address and the group address and the originating RP address. The RP address is the unique loopback, not the Anycast address. Remember that. This message is sent to all MSDP peers. Each peer receives it and runs a forwarding decision at that point. If an RP receives an SA and has interested receivers for that group, it triggers a join towards the source. If it has no interested receivers, it ignores the SA content, but it still forwards the SA to eligible downstream peers. And of course, it stores the entry in its SA cache. Let's watch this across facilities. A source becomes active in Glasgow, for example. Its designated router sends a PIM register to the nearest RP, RPC, for example. C installs an SCOMSG state and originates an SA message, a source address, group address, and the IP address of the RP. RPC sends that SA message to its MSDP peers, RPA and RPB. RPA in London has receivers waiting for that group. They are interested. It sees the source active message, it triggers an S-G join towards Glasgow, and traffic flows. Happy days. RPB in Manchester has no interested receivers for that group at this moment. Nobody right now. It receives the SA, it forwards it, it caches it, and no traffic pulled. But the knowledge is preserved. We know about the source, we know about the group, we know where to find it if we need it. Any receiver that joins in Manchester will find the source because the knowledge has propagated throughout the multicast domain. Let's talk a little bit about MSDP timers. Every one of them defines a boundary in your recovery window. In the SA advertisement, the timer defines how often source knowledge is refreshed. This is 60 seconds. Every 60 seconds, active RPs re-originate source active messages for their active sources. The SA state timer defines how long a cached entry survives without refresh. Must not be less than the SA advertisement. Period plus the SA hold down period. In practice, this means that cached entries survive long enough to weather one full advertisement cycle. So when the timer expires, the entry is deleted and the source disappears from that RP's knowledge. In practice, this means the following. Facility number 3 goes offline. RPC stops originating SA messages. London and Manchester have cached entries for Glasgow sources. Let's say Glasgow goes offline in our scenario. Then RPC stops originating source active messages. London and Manchester have cached entries for Glasgow's sources. Those entries have timers counting down 60 seconds minimum before entries start expiring. After expiry, sources registered to Glasgow's RP become invisible to London and Manchester. Not because the sources stopped, not because the routing failed, because the cache expired. New receivers in London asking for those sources will effectively get nothing. The peer hold timer defines how long before you know a peer is gone. 65 seconds is what the standards would recommend. If a peer goes silent, you wait 75 seconds before tearing down the session. After teardown, the connect retry timer start 30 seconds before the next TCP connection attempts. It's very similar to BGP. That's over 100 seconds before MSDP even begins recovering a lost peering. Remember that. Keep alive messages keep the whole timer alive during quiet periods. They are typically at 60 seconds. How does this play out in practice? If Manchester drops off the network, London and Manchester don't know immediately. They wait up to 75 seconds for the hold timer to expire. Then they begin reconnection attempts. The SA cache timer is running in parallel. Sources registered to Manchester's RP begin expiring from remote caches within that same window. Some incident reviews discover these numbers after the outage, not before it. Let's take a look at the state machine of MSDP so we can understand it deeply. MSDP has 5 states, 10 events, and 9 actions. When MSDP peering is configured, event 1 fires. Action 1, it allocates resources. It compares IP addresses to determine who listens and who connects. The higher IP address listens passively on port 639. The lower address connects actively. If both try to connect simultaneously, the lower IP is established. In the established state, the session is active. Keep alive TLVs are exchanged to keep the hold timer alive. When an SA arrives, 4 things happen. Hold timer resets, peer RPF check runs, and if it passes, the SA forwards to eligible peers, caches locally, and notifies PIM sparse mode. If it fails, the SA drops silently. A peer that is down is simply not in the consideration set. Remember that. So when a facility fails and peering drops, peer RPF recalculates immediately using only the surviving sessions. If we go back to our example, Manchester goes offline. London's MSDP peering with Manchester drops. Manchester is removed from the peer RPF check configuration. The SA messages that would have arrived via Manchester now need another path if your topology has one. If it doesn't, those SAs never reach London, and London never knows about the sources behind them. So what is this check for? This peer RPF forwarding is how MSDP prevents loops. When an RP receives an SA from a peer, it asks one question. When RPX, for example, receives an SA from a peer, call that N, it asks one question. Is N my correct peer towards the originating RP? If yes, accept it, forward, cache it. If no, drop it. That's it. There are 5 rules for this. Rule number 1, you have a direct peering with the originating RP. That peer is your RPF peer. Simple. Number 2, BGP exists. The eBGP next hop towards the originating RP is one of your MSDP peers. That peer wins. That is important. It ties MSDP peer selection to BGP topology in case you're running BGP. If you change your BGP topology without considering MSDP and peer RPF breaks. Rule 3. Route to the originating RP was learned via distance vector or path vector. The neighbor that advertised it is the RPF peer. Link state protocol, the IGP next hop is the RPF peer. Rule 4. Multiple peers in the same AS towards the originating RP. Highest IP address wins. And rule 5. Static configuration overrides everything. So let's walk through the practical example. We have 3 facilities, full MSDP mesh. Manchester goes offline. Peer RPF recalculates at London and Glasgow using the surviving peers. If your BGP and IGP topology supports a new RPF path between London and Glasgow directly, source knowledge continues flowing. If it doesn't, SA messages from Glasgow fail the RPF check at London. Sources registered to Glasgow's RP become invisible to London. Most networks have never drawn the peer RPF path for each facility-to-facility combination, or tested what happens when one node in the path disappears. In any cast RP deployment, all RPs are effectively MSDP peers. In a full mesh of 3 RPs, each SA message arrives twice at each RP. Mesh groups solve for this. Let's break this down. If you receive an SA from a mesh group member, the rule is to forward it only to non-mesh group peers. Don't re-advertise to other mesh group members. The originator already sent to all of them. The assumption is a full mesh, of course. Every member has a direct peering with every other member. In our 3 facility example, all in the same mesh group, if Manchester goes offline and RPB drops out of the mesh group, London and Glasgow lose one mesh member. They retain their direct peering with each other. SA messages between London and Glasgow continue. Manchester source fade from the cache as the SA state timer expires. This is the expected behavior if the mesh was designed for facility failure. If the mesh had gaps, the behavior is slightly different. That usually is undiscovered. Now let's take a complete facility failure walkthrough. Before the failure, everything is working as expected. 3 RPs, full mesh group. Source knowledge is shared across facilities. A receiver in Glasgow can find S1. It's in the SA cache at RPC because RPA originated an SA and it propagated. A receiver in London can find S3. Same reason in reverse. Everything is operating as designed. Now let's say Manchester goes offline. RPB drops, its links go dark. The IGP starts withdrawing RPB's routes. The Anycast RP address was being advertised by 3 RPs. Now it's being advertised by 2. Sources near Manchester Manchester lose the route to their nearest RP instance. After your IGP reconverges, their DRs find the next nearest RP, depending on the topology. That's RPA in London or RPC in Glasgow. Those DRs begin sending PIM registers to the new nearest RP. London and Glasgow don't know Manchester is gone yet for 75 seconds. The whole timer hasn't expired. The keep alive messages fire. No response comes back. The SA cache still holds S2 entries, Manchester's sources, effectively. The SA state timer is counting down from the last SA received from RPB. During this window, existing receivers can still receive S2 traffic because the multicast tree has already been built. The source data flows independently of MSDP state once the tree is established. The problem isn't existing flows, unfortunately. The problem is new joins. At 75 seconds, the whole timer expires. The event 8 fires at both London and Glasgow. The TCP sessions close. RPB is removed from the peer table, removed from peer RPF consideration too. The connect retry starts. Reconnection attempts begin every 30 seconds. They will fail until Manchester recovers. Now, peer RPF calculates at this point. London and Glasgow have a direct peering that survives. SA messages between London and Glasgow continue without interruption. In this window, this is the moment I have seen some organizations haven't measured. S2 entries expire from the SA cache at London and Glasgow. Existing receivers watching S2 are fine. Their S, G are built traffic flows. MSDP state doesn't affect established multicast trees. But a new receiver in London is joining S2's group, finds nothing. RPA has no source active for S2. No join is triggered. Whatever feed that is, it doesn't appear without an error message. And the answer when someone eventually is that the source active cache expired. Recovery comes from the sources themselves. Manchester's DRs lose the route to RPB. IGP reconverges, DRs find the new nearest RP. They start sending PIM registers to it. The new RP installs S, G state and originates new SA message. That SA propagates to London and Glasgow. S2 reappears in the SA cache. New receivers can now find it. The recovery window is not the RP failover time. It's not the link convergence time. It is effectively IGP convergence plus PIM register plus MSDP SA propagation combined. It is something you can measure. I've seen designs that have never measured this. They don't know. Now let's put it together. At 0, Manchester goes offline. Immediately after, the IGP withdraws route. DRs begin re-registration. At 75 seconds, whole timer expires. MSDP sessions torn down and the connect retry begins. At cache expiry, S2 disappears from remote SA caches. It equals IGP plus PIM convergence plus Manchester sources re-register to surviving RPs. SA propagates, sources reappear. New receivers during that gap cannot find Manchester's sources. Existing receivers unaffected. How long is that gap in your network? If the answer is we don't know, that's the conversation you might want to have. Every mechanism we have just discussed protects an assumption. Remember that Anycast RP assumes another RP instance is topologically reachable when one fails. MSDP assumes peers are in established state and exchanging SA messages reliably. Mesh groups assume the full mesh remains intact when a member disappears. Multi-facility designs assume that peer RPF paths survive facility level failure. These are not unreasonable assumptions, to be honest. They are just untested assumptions. And the difference between those two things is where operational risk lives. MSDP will reconverge after facility failure. The validation question is specific. What is the peer RPF path between each surviving facility pair after the failed facility is removed? You can draw it on paper, but paper doesn't can't run peer RPF checks, unfortunately. But there is a simple test. Isolate one facility. Verify that source active messages still propagate between the remaining two, and then measure the time from isolation to SA repropagation and compare it to your operational SLA. If you've never run this test, then you might not know whether the assumption holds. Sources re-register correctly after their local RP fails. The validation question is, how long does that actually take? It's not one timer, it's actually 4 timers in sequence. IGP reconvergence, PIM register retry, a new RP SA origination, and MSDP propagation. The test is as follows. Remove the RP from one facility, measure the time from RP loss to source reappearing in the SA cache of a remote facility. That number is your actual source recovery window, not the theoretical on paper one, not the unlikely to be the one in the design document too. And the third one, facility isolation behaves as expected. This is the assumption most designs I've seen never actually test, because testing it requires deliberately isolating a production facility or building a test environment that accurately reflects the production topology. That validation question is what exactly happens at each remaining facility when one disappears completely. Not partially, not briefly, completely. The test involves isolating a facility at the WAN boundary and observing multicast behavior everywhere else, measuring SA cache expiry windows and verifying peer RPF calculations, verifying source to register, and documenting that workflow, that timeline. The result of that test is your resilience posture, not the intended one, the real one. What this means at a facility level then. Infrastructure directors who have run this test can answer incident review questions with actual measured accurate data. How long before sources were rediscovered and measured, which receivers were affected and for how long, documented, and whether the architecture proposed behaved as designed and verified. Infrastructure directors who haven't run this test answer those same questions with uncertainty. Those are two very different conversations across the board. When I'm reviewing a multicast architecture for a broadcast network, 5 questions tell me more than any forwarding diagram. Are MSDP peerings using unique unicast address? Is the anycast address absent from the SA messages? What is the whole timer and does it match the network's convergence tolerance? What is the worst case SA cache expiry window per facility and has it been measured? Has facility isolation been tested end to end? The first 2 are configuration questions. The third is a fine-tuning question. The fourth and the fifth are the validation questions. Most designs I have reviewed in the past year maybe could answer 1 to 3. Almost none could answer 4 and 5 with accurate measured data. That gap is where the risk is. Anycast RP reduces a failure domain. MSDP preserves source visibility. Mesh groups reduce SA flooding. All 3 are well specified, well understood, and well documented. None of them make an architecture resilient on their own. Resilience is effectively the gap between what was designed and what was tested. And in multi-facility broadcast environments, that gap is usually larger than anyone realizes, until it surfaces in an incident review. At that point, question isn't how the protocol actually works. The question is why the behavior didn't match the expectation. And the answer is almost always the same. The assumption was never rigorously tested. And if you're operating multicast across broadcast facilities and you want to close that gap, ask a question, reach out. That's it. Thanks for watching.